The first talk is by Dr. Rashid Ganeev, who is the current ERA chair here at University of Latvia, and he will take us through some recent developments in nonlinear optics in Latvia. So please go ahead, Rashid.
Yeah.
Welcome.
Okay. Thank you very much, Suna, for giving me this chance to present our recent studies in nonlinear optics. Let me say a few words prior to sharing my slides about the history of this recent developments. In 2020, European Commission awarded University of Latvia with European Regional Development Fund. And this fund was the basis for the creation of ERA chair in University of Latvia. And I was chosen as ERA chair holder, and starting from 2021 till now, I am developing a field of nonlinear optics. We created a laboratory of nonlinear optics in Institute of Astronomy at University of Latvia, and trying to study different issues of nonlinear optics, which can provide some sort of merger between quantum processes and photonics. And in my presentation, I will discuss some new findings in this field. So let me first share my screen. Is it seen?
Yeah.
Yeah, okay. So the topics of this presentation is...
So sorry, it's not yet full screen, so can you...
But I put it full screen.
Probably you shared not your screen, but this presentation only. Better share your screen.
Share my screen. Okay, let me... So, is it this now?
Yes.
Yeah, okay. So, let me say a few words about previous studies of nonlinear optics in Latvia. Of course, there were some rare options in studies of nonlinear optics. However, for nonlinear optics, one needs to have strong lasers, as well as some motivation in studies of new samples, newly sensitized samples for practical and fundamental applications. During my presentation, I will show some new samples, which allows us to expect that those samples, the nonlinear optical properties of those samples will be very attractive for some practical applications, both in fundamental science as well as in lasers and so on. The topics of my presentations are basics of nonlinear optics. I will briefly tell a few words about these topics of optics. Then I, in details, will present recent developments of the nonlinear optical studies of molecular and quantum dot species, which were synthesized during last time in different laboratories. And finally, I will talk about perspectives of strong laser meta interactions, which we now developing in the collaboration with many laboratories worldwide. So, the basics of nonlinear optics represent some sort of the fields which were during last 50 years developed in different laboratories, and they presented, not all, but some of them are presented in this list. And what's the difference between nonlinear optics and linear optics? In the case of linear optics, the response of polarization, frequency, and other parameters of laser beam is linear to the intensity of or electric field of laser radiation, contrary to the case of the nonlinear optical effects, when both frequency, path of laser radiation, its phase, polarization modifies nonlinearly, and it gives many interesting effects which are shown below. Here, I do not want to talk about all those effects, but I just by bold shown the fields which we're trying to develop in Latvia, and those include third harmonic generation in different media, high order harmonic generation, some frequency generation, optical parametric generation, optical parametric amplification, nonlinear light matter interactions with free electrons and plasmas, optical Kerr effect and part of its self-focusing, cell-phase modulation, and multi-photon absorption. I will talk about almost all of these topics during my presentation and show how we develop those fields in the laboratories of University of Latvia and other laboratories about which I also will talk briefly. So the topics are as follows of all laser matter interactions. Here, I just show the scale of laser intensities between 10 to 0 up to more than 10 to 20 watt per square centimeters. There are many fields of laser matter interactions. I did not put, of course, all of them, but I just show the range of nonlinear optical effects which occur in the range below 10 to 8 and above 10 to 20 watt per square centimeters. And by bold, I marked those fields which are of our interests, and I will tell about them more in details. Particularly, we are working with clusters formation for nonlinear optical studies, analyze low-order nonlinearities and surface nonlinearities, and especially interested in plasma and gas harmonics generation. So now I start to talk about the developments of studies of some molecular and quantum dot species. First of them is the species which is very important for the studies. Sorry, it is maybe, sorry, So the first species is a carbon disulfide. Carbon disulfide is a well-verified liquid for calibration of the nonlinear optical processes using Z-scan technique. Z-scan technique is just shown here. It is a method for analysis of nonlinear absorption and nonlinear refraction in materials. Laser radiation scheme is exceptionally simple scheme. Laser radiation focuses inside the sample, and using so-called open aperture and closed aperture schemes, we can analyze respectively nonlinear absorption and nonlinear refraction. Why this material is interesting for the researchers? All nonlinear optical studies of materials are mostly calibrated using carbon disulfide. However, in most cases, they use the calibrated values at only at 800 nanometers, which is the most useful laser wavelengths in the case of femtosecond lasers, or 1064 nanometers, which is the wavelength of YAG laser. However, this liquid has a very broad range of variations of nonlinear optical parameters once you change the driving and probe radiation. In that case, it's necessary more closely analyze the processes which appear in the case, especially in the case when you use short wavelength radiation. Here I just show some classical formulas which are used for the analysis of the normalized transmittance of carbon disulfide, and just show here the option when in case of short wavelength radiation, very important effect starts to appear is a 3-photon absorption, which is rarely absorbing in other materials, and in some cases 3-photon absorption becoming stronger than 2-photon absorption, and especially it become strong in the case of near-infrared radiation and above 1000 nanometers, for which we use some specific formulas to feed the results and analyze the characteristics of 3-photon absorption. We analyzed both nonlinear refraction, which is classical dependence of nonlinear of normalized propagation through this liquid, which shows a positive sign of nonlinear refraction, and we analyzed the dependence, wavelength dependence of this parameter. Notice that these measurements were done using 28 picosecond probe pulses. In that case, this molecular medium shows not only electronic Kerr effect, but also molecular Kerr effect and orientational Kerr effect, which provides more rather stronger nonlinear optical response with regard to the femtosecond probe pulses. We analyzed the spectral dependencies, and now these dependencies can be used as a calibrated values for different nanosecond picosecond pulses once they calibrate them to analyze the nonlinear optical properties of other materials. We also analyzed the nonlinear optical properties of this liquid using 150 femtosecond probe pulses. One can see in this dependence of the Z-scans on the wavelengths that the normally observed positive nonlinear refraction becomes negative refraction in the case of the 400 nanometer radiation. Why it happened? We analyzed this dependence in the case of short wavelength radiation and increased intensity of probe radiation. Initially, just shown the classical positive nonlinear refraction, and with the growth of intensity of probe radiation, it became significantly transformed, and finally, at higher intensity, it just shown negative nonlinear refraction. It means that in that case, we have addition of the higher order nonlinear optical process, 5th order nonlinear optical refractive index. In the case of 800 nanometers, we determined this value, and this value can also be used once the researchers study the nonlinear optical properties of materials in the UV range. Another material is the quantum dots films. We analyzed mercury telluride quantum dot films as well as other quantum dots and some nanoparticle films to create the samples which could be used for practical applications like optical limiting and mode lockers for lasers. The first sample is Mercury telluride quantum dots with the sizes of a few nanometers. We use it with 3 to 4 nanometers quantum dots, which have shown the spectral dependence of the nonlinear absorption process, which is saturable absorption, and nonlinear refraction. This dependence is also important to understand where the nonlinear optical processes could be used most efficiently. Particularly, the saturable absorption was absorbed at roughly 700 nanometers as the strongest nonlinear optical effect. Thus, correspondingly, it could be used for the mode locking of femtosecond lasers in this wavelength range. We also analyzed this process in the case of femtosecond 150 femtosecond pulses, and observed that the nonlinear absorption process growing in the case of close to 400 nanometers, which is obvious that the nonlinear optical absorption increasing due to the more efficient two-photon absorption. The studies were carried out using both picosecond and femtosecond lasers, which were tunable in the broad range, and we have shown that those quantum dots can be used for in different fields, and particularly as the mode lockers for lasers. Moreover, we expect that those quantum dots could be used as efficient emitters of high-order harmonics. Why such expectation could be realized in some more sophisticated systems? It is due to the appearance of interesting effects like quantum confinement, once those quantum dots appearing in the shape of plasma during propagation of strong laser pulses through such medium. Later I will talk on that more in details. Other studies are related with exfoliated nanoparticles. Bismuth telluride is well-known and developed nanoparticles. Those exfoliated nanoparticles are used for optical limiting, for mode lockers, Q switchers, and some other applications. However, like in all previous cases, information about them was only in the range of 800 nanometers. We determined that saturable absorption in those exfoliated nanoparticles becoming more stronger in the case of visible range, particularly for 500 nanometers. And we expect that in that case, we can use these films for the creation of femtosecond sources using modulation of the process in picosecond oscillators to create femtosecond pulses. We analyzed the properties of those materials and in the broad wavelength range and intensity range, and found that saturable absorption and nonlinear refraction play very important role in the case of those nanoparticles and can be used for some interesting applications. And one of them is, as I told, is the mode lockers. How to do this? We created thin films, like in case of Mercury telluride, and we can just insert them in the oscillator and in that case, just directly can create the train of femtosecond pulses. Another quantum dots are the Mercury sulfide quantum dots. Those quantum dots also have interesting properties, and many groups working with those quantum dots also for different applications, and particularly for third harmonic generation. Meanwhile, we analyzed the spectral dependence on third harmonic generation. In that case, the scheme is as simple as in the case of Z-scan. Femtosecond laser propagates through the sample, which place it in the focus, and we analyze third harmonic signal in that case. You can imagine we use it very thin films of those quantum dots, and just shown that the efficiency of third harmonic generation is quite strong, the range of 10 to -4, while the thickness of those nanoparticle film are in the range of few hundreds nanometers. And those nanoparticles also have small sizes in the range of 3 to 4 nanometers, and the spectral dependence and intensity dependence were analyzed during our studies, which can be useful for the practical applications of those films. Our analysis of third harmonic generation shown the spatial distribution of the third harmonic signal in the case of 70 nanometer thick mercury sulfide thin films placed on the glass plate. We have shown that from the pure glass plate, which has the thickness much more higher, it is around 1 millimeter, we have also very small signal. While for 70 nanometer thick film, we have much more stronger, and overall the ratio between those signals becoming a few orders stronger in the case of those films compared to the glass film. And those pictures just show spectral dependencies on the different parameters like conversion efficiency of third harmonic generation and ratio of signals of third harmonics. My third part is related with the perspectives of strong laser-matter interactions. I will show some samples of our first studies when we analyzed it in our joint collaborative studies the laser plasma characteristics for the creation of the optimal medium for high order harmonic generation. And we compare the properties of plasma at different conditions of ablation of targets with the required conditions for efficient high order harmonic generation. In few words, third harmonic generation on the language of photons shown is there. You have a few photons which provide the strong photon with the energy equal to photons. So how this process occurs? Amplified femtosecond laser pulse propagates either through the gas jet or laser plasma, specially prepared for those cases, and then X-rays in the range of extreme ultraviolet range, it is around 10 nanometers, analyzed by the XUV spectrometer. Another interesting feature is harmonic generation in molecules, high-order harmonic generation in molecules. Once electron accelerated in the strong field, returns back to another atom of molecule and creates high-order harmonic generation, which differs from the HgTe high-order harmonic generation from atoms. Here I'll show some samples. Once we used the laser plasma for high-order harmonic generation. The scheme is as follows. First, picosecond pulse from the amplifier creates plasma on the targets placed in vacuum. Second, after second beam, after propagation of the grating compressor and delay line focuses on this plasma at specific delay with regard to the heating process, and generating harmonics are analyzed in the XUV spectrometer. And common rough picture of the harmonics is shown there, where here you show lowest order harmonics and here highest order harmonics. We need to analyze this plasma as well, because of just creating the plasma by thinking that creating stronger plasma by stronger heating pulses does not provide efficient high-order harmonic generation. Because of this, we also analyze creation of plasma and then analysis using intensifying CCD camera, which allowed us analyzing the dynamics of plasma spreading from the out from target, as well as analyzing the spectrum using the spectrometer with higher spectral resolution. Combination of those systems allows us determining the best conditions and best ways for high-order harmonic generation. Here we show the 3D images of spectra in the visible range, particularly in case of chromium, ablated chromium, and also using this spectra, we were able analyzing the electron temperature and concentration of electrons as functions of delay between heating and further decaying of plasma. Once knowing the concentration of free electrons, we optimized the delay when concentration of free electrons, which are plays very negative role in the high-order harmonic generation due to creation of phase mismatching conditions. We found some delays at which most efficient generate the high-order harmonics. So we used this results for generation of harmonics in chromium using different lasers, particularly in case of 800 nanometers, we observed strong resonance harmonic for 29 harmonics, which significantly differs from the other low-order harmonic, which is unusual in the case of high-order harmonic generations, which commonly in case of gases shows featureless plateau-like shape. In that case, we used very narrow size of laser plasma, as well as we used 1300 nanometer radiation, which shows the same feature in the same spectral range, which shows some enhanced harmonic in the extreme ultraviolet range. Similar picture was observed in the case of generation of extended plasma. Once we generated both odd and even harmonics, however, we were not able to observe resonance harmonic, which is out of this scale, due to some quasi-phase matching conditions, for this harmonic in the case of extended plasma. And to overcome these problems, we use a multi-slit mask to create a few multi-jet plasmas to observe this resonance process. Thus, we have demonstrated the method of laser-induced plasma formation and its characterization for efficient high-order harmonic generation. In the case of chromium, we observed appearance of the resonance harmonic, which is unusual for the case of high-order harmonic generation and cannot be considered observed in the case of gases, and it is a feature of this material. Thus, we just shown that this method of high-order harmonic generation creates not only the source of extreme ultraviolet photons, but also can be used for the material science in the extreme ultraviolet range. Another materials are indium and tin laser-induced plasmas. Those two plasmas were early analyzed, and it was observed that they can provide very strong high-order harmonics generation, and especially some single harmonics which are much more stronger than neighboring harmonics. So to determine the best conditions for those processes, we also analyzed the properties of plasma in our laboratories and created the conditions when such materials allows us generating very strong resonance enhanced single harmonics, which can be useful for analysis of some materials in the XUV range below 100 nanometers. How we done this? As I have shown in previous cases, we analyzed the dynamics of plasma spreading in the case of indium and tin, and found the optimal conditions. It was around 100 nanometers. It is nanoseconds. It is a delay between picosecond heating pulse and femtosecond driving pulse. And at these conditions, we found the optimal, best conditions of high-order harmonic generation. We also, using the spectral characterization of plasmas, analyzed the electron temperature and concentration of those plasmas and found the optimal conditions for the from the point of view of delays for those parameters, and obtained at those optimal conditions the high-order harmonic generation, particularly in case of tin, when using 1600 nanometer radiation, we observed enhanced single harmonic in the range of 34th harmonic of 1600 nanometers. Similarly, once we use a 2200 nanometer radiation, we observed the same process when the strong 47th harmonic became much more stronger than low order harmonic, which is unusual process for the high order harmonic generation. The same we observed in the case of the indium plasma. Here I show some image of plasma spectrum, then generation of single harmonic in case of 800 nanometers in indium plasma. This slide shows the generation of single harmonic and also enhanced harmonic in the case of two-color pump, when enhancement of this harmonic becoming not so strong compared to the neighboring harmonic in the case of single color pump. And in the case of near-infrared laser radiation, I have shown that this harmonic still becoming very strong compared with many other harmonics and can be used as a source for some other nonlinear optical processes in XUV range. Here just shown the pictures of strong resonance harmonic in the range of 62 nanometers in case of indium plasma, once we use 2100 nanometer, and the same in the case once we use the 800 nanometer radiation. Overall ratio between this harmonic and neighboring harmonic becoming in the range of 100, which is quite sufficient to consider this harmonic as a single coherent source of radiation. Thus,
3 minutes to go, Rashid. 3 minutes.
Yeah, okay, I'm completing. So those studies just shown us that by analysis of the properties of plasma and combining them with features of some materials, we can observe very interesting processes. For example, here I just show a Hassel harmonic from indium, and the same in manganese plasma, which shows the blue shifted high order harmonics in that case. I do not want, I have no time to discuss this, but I can just say that optimization of plasma allows us creating the very good and bright high order harmonics. And I share some preliminary results which I obtained a couple of weeks ago in Münster University in collaboration with Helmut Zacharias and Victor Karcher. Probably some words will be said in the next presentations. We used argon gas and generated high-order harmonic generations. It is common picture for lowest order and highest order harmonics up to 23rd harmonic in case of gas plasma. Nothing special. However, once we inserted the S-wave plates, which created the radially polarized beam, which have shown this donut-like shape. We observed together with insertion two BBO crystals, very interesting pictures, which significantly differ from the common picture. They were divided due to some specific phase processes and phase mismatching processes along the divergence range, and we see how odd harmonic generate such shapes and even harmonic generate those shapes. Once we use it, the azimutally polarized beam, which also have this donut-like shape, we see again normal distribution of harmonics, which can be again compared with the radial shape and show the difference between this process. We yet analyze this because it is a complex process of interaction of three beams. Second harmonic generated by fundamental beam and also using very thick crystal, and second harmonic generated but very thin beam, and their interaction in plasma is very interesting and required additional consideration. And some interesting result observed in the case of so-called SPP plates, those are spiral phase plates. When once you have compare them with ordinary Gaussian beam, you can see that they significantly divided by two parts, which is just shape of the vortex beams in the case of donut-like shapes of vortex beams in the XUV range. We expect our collaboration with many laboratories of both in Latvia, and significant role in those studies were in Institute of Solid State Physics. We also started studies with Münster University, and in June we all continue in details analysis of those processes, not only in gases but in plasma. We have some preliminary discussion on that matter with Lund University and hope to make similar experiments using the Picosecond facility. And we have agreement with Changchun Institute of Optics in China, Max Born Institute in Berlin, and Imperial College in London. Summarizing, I would like to say that nonlinear optical studies started well developed during last 2 years. We published it in Q1 and Q2 journals, a few papers, maybe around 10 papers on that matter, and found very interesting features which can find further developments during our collaboration with different teams. I would like to say that those studies could not be realized without European Regional Development Fund and some other funds which I included in this funding section. And I would like to thank many my colleagues who worked with me in this field. Thank you very much for your attention.
Thank you, Rashid, for a very nice overview. And it's very reassuring to see how strongly nonlinear optics is developing here at University of Latvia in a very short time. Congratulations, Rashid, to you and to your very competent collaborators. Any short question before we proceed?
I'm wondering what will be the maximum electron temperatures you can reach?
Electron temperature, we can achieve higher than electron temperatures up to 10 eV, but it is not useful for high order harmonic generation. This was how to say some sort of mistake for first experiments which were carried out in many laboratories in 90s. Once we created very strong electron tank, people created very strong temperature and very high concentration of plasma. In that case, we have very strong concentration of free electrons, which fully kill the process of high order harmonic generation. Because of this, we intentionally decreased the temperature of electrons up to 1 or 2 electron volts and worked at these conditions. How to do this? We just used some delay between heating and driving pulse. In that case, we can create conditions when the concentration of particles, active particles, are still strong, but concentration of free electrons and their temperature becoming lesser than the conditions when phase mismatching processes start to occur.
Question, Rashid. When you enhance strongly a particular harmonic, is that mainly a question of optimizing the quasi-phase matching, or is it also some resonant feature in the particular species you are making a plasma on?
Yeah, good question. Thank you. It is second, not first. If it was first, it could be observed in the case of gas harmonics. But it is special feature of plasmas. In the case of gas harmonics, you have only a few harmonics, from noble gases, and they are featureless, all harmonics. They just show the plateau-like shape. In the case of solid materials, a few solid materials, maybe 10 materials among the whole periodic table of non-radiated materials, can create resonance harmonic. It is just feature of the specific transitions possessing strong oscillator strengths. These strong oscillator strengths create conditions for best enhancement of single harmonic generation. Of course, some neighbor harmonics also enhancing, but the nearest harmonic to this transition becoming very strong. And initial studies on this field were carried out by different teams around the globe, and the information about this oscillator strengths helps us to achieve those good results. It means that this method is just method of material science in XUV range.
Thanks a lot, Rashid Ganeev, for an excellent talk. Thank you very much.